In this video, I'm going to talk about how you can use MATLAB to convert a continuous transfer function into a discrete one using various methods that we have covered in this section, which is section 5. But before that, let me just give you one final example on using the ZOH or hold equivalence method. So there was an example in the notes of series RL circuit. So a series RL circuit would be something like this, where you have a resistor in series with an inductor. So, and then you have a voltage input. So what we are trying to do is we are trying to measure by supplying an input voltage here. We are trying to measure the output voltage across the inductor. So for this particular circuit, the equation would be something like this. So V, which is the input voltage, would be equal to VR, the voltage across the resistor, plus VL, voltage across the inductor. So the voltage across the resistor is I times R. So I is the current flowing in this circuit, plus voltage across the inductor is given as L times di over dt. Now if you convert this into, if you do a Laplace transformation of this, you would get V of S is equals to R times I of S plus L S times I of S. So probably this I should be capital. Now we know that if you want to convert this filter into a transfer function form, then we know that a transfer function is equal to output over input. So the output is VL, voltage across the inductor, and the input is V. So if we do a transfer function g of s is equals to VL over V, we will get, so VL is L times di over dt, which is Ls times capital I of S. So over here it's Ls times capital I of S divided by V is R times I of S plus L times S times I of S. So if we further simplify this, we will get Ls over R plus Ls. And after further simplification, this would be S over S plus R over L. So this is our transfer function for this particular filter. Now, if you want to convert this filter into a discrete filter by using the ZOH method, the first thing you would do is do GS over S. So GS over S would simply be 1 over S plus R over L. Then we would need to do Z transform of GS over S. So if you do Z transform of GS over S, so this is a simple transfer function. So using a Z transform table, you can see the result would be Z over Z minus e to the power minus R over L times T. So in this case, I is R over L, so it would be minus R over L times whole thing times T. Now we need to multiply Z transform, this Z transform with 1 minus Z to the power minus 1. So if you do that, this would simply be, if you convert this into Z, it will be by multiplying all the terms by Z over Z, then this would be Z minus 1 over Z. And then multiply it with this equation, you will get Z minus 1 over Z minus e to the power minus R over L times T, which is also equal to, if you divide all the terms by Z, it would be this, and this is the same result that you get in your notes. Now moving on to using MATLAB for converting a continuous system into a discrete one. We have been using this example in our notes. So the example is h of s is equals to I over s plus I. So let's say we now substitute 1 as I. So we will get h of s is equal to 1 over s plus 1. And throughout, let's say our sampling time is 0.1 seconds. So the first method that we are going to look at is the whole equivalence method, which is the zero order whole method. So using this method, we got the result as h of z is equals to 1 minus e to the power minus I times capital T divided by z minus e to the power minus I times t. So if you substitute I and t, we would get the result as 0.0952 divided by z minus 0.9048. Now let's see if we get the same result using MATLAB. Now in my MATLAB, I have defined a system C as 1 over s plus 1. So this is a continuous time transfer function. To convert this continuous transfer function into a discrete one, we will use the MATLAB function C to D. So my system D is equals to C to D. The first input would be my system, continuous time system, so which is sys C. The next input would be the sampling time Ts, which is 0.1, and method. So for the first method, which is whole equivalence, we would specify over here Z or H. So we are going to use zero order whole method, which is what I have shown you in the example. So when I do that, when I run this function, I get my system D as 0.09516 divided by Z minus 0.9048, which is the same result that I got using the worked example, which is here. So this is the same result as my MATLAB result. Now moving on to the second one, which is pole zero matching. So using this method for this particular transfer function, I got the same result as using the whole equivalence method, which is finally when you substitute A and T, we got 0.0952 divided by Z minus 0.9048. Usually this would not be the case, so it would be different. So it depends on the transfer function in h of s and other variables such as t and so on. So let's go to MATLAB and see what result we get for this particular method. So if I want to use the pole zero matching method, I can use the same function C to D. So sys is equals to C to D. Transfer function is sys C. Sampling time is 0.1, and my method would now be matched. So this is pole zero matching method. So when I execute this, I get 60 as 0.09516, which is 0.0952 divided by z minus 0.9048, which is the same as when using the Z or H method. Next, let's look at the bilinear rule. So let's look at the bilinear rule, which is also Tustin's method. So using this rule, we got h of z is equal to I over 2 over t times z minus 1 over z plus 1 plus I. And if we substitute I and t, or this would further simplify to I times z plus 1 divided by 2 over t times z minus 1 plus I times z plus 1. So if we substitute I and t, we would get z plus 1 divided by 21z minus 19. And if we divide all the terms by 21, so that we just have z here in the denominator, we would get 0.0476 times z plus 0.0476 divided by z minus 0.9048 in the denominator. So this is what we would get. Now let's see if we get the same result using MATLAB. So in MATLAB, if we want to do bilinear transformation, we can use the method Tustin. So sys D is equals to, again using C to D function, sys C, sampling time is 0.1, and my method is now testing. So when I execute this, I get 0.04762 Z plus 0.04762 divided by Z minus 0.9048, which is the same result that we got by working it out by hand. Now let's look at the last one, which is impulse invariant method. So impulse invariant method, using impulse invariant method, we got the result as Iz of Z minus e to the power minus it, and if we substitute I and t, we get Z over Z minus e to the power minus 0.1. Now for the impulse invariant method, after we get h of z, we have to multiply this by t. So this is a step that we missed out in the notes, where you have to multiply this z equation by t. So if we do that, we will arrive with the result 0.1 z divided by z minus 0.9048. So this is the result that we should get. Now let's look at MATLAB. Now in MATLAB, using the C to D function and using the method impulse, we can get the impulse invariant equivalent transfer function in Z. So again, sys D is equals to C to D, sys C, sampling time 0.1, and my method is impulse. Right, so when I do that, I get my sys D as 0.1 Z divided by Z minus 0.9048. So this is my result using MATLAB.